watching it out there on webland. The Apollo program was a project that put 12 people on the surface of the moon over 6 missions, and it's been called mankind's greatest technical achievement because it was an enormous project, very, very complicated, and it required the development of a number of new technologies that all had to work together, and it was very successful. And the technological legacy of Apollo is pretty tremendous. For example, computer technology was advanced in several fundamental ways, partly as a direct result of Apollo. And there were other technologies like manufacturing and communication and spaceflight itself. I mean, would it be so routine to put satellites into orbit around the Earth if it had not been for this huge injection of resources into spaceflight in the 1960s? So the technological legacy of Apollo is huge. I want to talk more about the scientific legacy. That is, what has been learned about the Earth and the Moon and the solar system as a result of the scientific research done during the flights. So that's what I want to concentrate on. And first, I want to talk a little bit about the inception of Apollo, what motivated it, because this is a symposium about the 60s, and a big part of the 60s was the Cold War, and Apollo was a manifestation of the Cold War. So a big turning point in the history of Apollo was a speech given by President Kennedy to Congress in May of '61. And it was a special address to Congress. It was essentially the second State of the Union address of 1961. It was that big a deal. And it came 3 weeks after Alan Shepard's flight into space. Alan Shepard was the first American to fly in space. He flew on what's known as a suborbital flight. His spacecraft went out of the atmosphere and came straight back down like a cannonball. And that occurred about a month after Yuri Gagarin's flight into space. He was the first person in space. He was a Soviet citizen, and he orbited the Earth. The Soviet Union had a much larger rocket than the U.S. did, and it had the capability of putting a manned spacecraft all the way into orbit around the Earth, which is considerably more difficult than just popping it up into space. So many Americans felt as though the U.S. was behind the Soviet Union in manned spaceflight. And it wasn't just a matter of national pride. After all, it was Cold War technology that put these people into space. These rockets were not developed to send people into space. They were developed to send nuclear warheads to the other superpower. And it was felt that a lead in manned spaceflight would equate to a lead in Cold War strategic nuclear capability. So you can see just what a Cold War deal it is if you look at the speech. This is a typed, a scan of one of the typed pages of his speech, and can't really see this too well. Here's a line that most of us are probably familiar with. I believe this nation should commit itself to achieving the goal before this decade is out, of landing a man on the moon and returning him safely to the Earth. No single space project in this period will be more impressive to mankind or more important for the long-range exploration of space. The idea of impressing mankind is important because at the time, the U.S. and the Soviet Union were locked in this power struggle, and each was trying to convince the other nations of the world to be on their side in this global polarization of power. Look at the sections of the speech. Defense of freedom throughout the world, economic and social progress at home and abroad, worldwide struggle for ideals, our partnership for self-defense, our own military and intelligence shield, civil defense, disarmament, and then space, where this page appears in the speech. So this is a Cold War speech culminating in the suggestion of putting people on the surface of the moon as part of a solution to the challenges faced by the U.S. in the Cold War. There's a line a few paragraphs later. It is the most important decision that we make as a nation, but all of you have lived through the last 4 years and have seen the significance of space and the adventures in space. And no one can predict with certainty what the ultimate meaning will be of mastery of space. So they didn't really know where spaceflight was going, but it was assumed that it's such a technological achievement that it would be important, especially in the Cold War. So Apollo was a Cold War project, and as such, it was very generously funded. And I think an appropriate symbol of the scale of the effort is the launch vehicle. This is the Saturn V rocket. One of these was used to launch each of the 6 landing missions, and there were 7 others launched, all but one of which was launched for mission preliminary to the landing missions. And at liftoff, this vehicle weighed 3,000 tons. That's almost 100 times heavier than the liftoff weight of the rocket that Alan Shepard flew on. So when Kennedy gave this speech, that's the increase in scale that they were looking at. And it wasn't just an increase in scale. Alan Shepard's spacecraft had to keep him alive for 15 minutes and allow him to survive re-entry. Now they had to have 2 spacecraft that operated in space for weeks and could navigate 250,000 miles to the moon with pinpoint precision, otherwise you crash. And they had to go into orbit around the moon. One of them had to descend to the surface against the moon's considerable gravity, soft land on the surface using rocket engines. They had to be able to get out, get back in, lift off again, go back up into orbit around the moon, dock with the other spacecraft, and then use that to come all the way back to the Earth and enter the Earth's atmosphere at 25,000 miles an hour and not die. So the technological development for all of that had yet to be done when Kennedy delivered this speech. So they were looking at an enormously complicated project. And it's hard to imagine how it could have been done had it not been funded with the scale of a Cold War project. But it was successful, and here are the 6 landing sites where the 6 landing missions landed. They're numbered with the Apollo mission number of the ones that landed. And they all landed on the near side of the moon, the side of the moon that always faces the Earth. That was done so that they could remain in radio contact with the crews on the surface without having to relay the signal through some other spacecraft. And they were all relatively near the equator of the moon. There's very compelling scientific reasons to go to the poles of the moon, but that's more difficult for reasons having to do with orbital mechanics. But they wanted to go to a variety of places because although it was a Cold War project, the missions were flown as missions of scientific exploration. And so they wanted to hit a variety of spots to get a variety of samples of material and study the surface in as much detail as possible. For example, you see the different shades of gray that the moon's surface is colored. That's a result of different rock composition. The dark stuff is mostly volcanic basalt, and the lighter stuff is a general type of rock called anorthosite. And they wanted to sample as much as possible many different areas. I'm going to explain why they wanted to sample these different areas. I'll show you one of these landing sites. This is the Apollo 15 landing site. Here's the landing vehicle. Here's an astronaut. He's got his backpack. And this is the lunar roving vehicle. There was one of these on each of the last 3 landing missions, Apollos 15, 16, and 17. And this thing was designed to fold up in a little cube, and it was packed, I think, in this place right here. You can see it's kind of been taken out. They could remove it, and it would unfold and kind of snap into place, and then the astronauts connected these peripheral items. And that's the way a lot of the equipment, the scientific research equipment, was taken to the surface. You can see another place over here where there's stuff still packed on the descent stage of this. This landing vehicle, here's the descent stage. It had its own rocket engine and rocket propellant. And the commander would land that on the surface, soft land it on the surface, and then that would be out of propellant. And the ascent stage had its own rocket engine and propellant. That's how they got back up into orbit around the moon. So I'll show you where this is on the moon. You can see the mountains in the background. Hopefully this is going to work. This computer's working really slow. Oh, doggone it. I don't know what's going on here. I don't know what it's doing. Something's preoccupying this computer. Okay, I'm trying to, it's just moving really, really slow. Well, I want to fire up a film, and then, you know, it's just real clunky. Like it's got something going on. What's it? Yeah, but it took off. I thought it was fixed. That's not what I wanted to show, sorry. Here's what I wanted to show. Okay, here we go. So I'm zooming in on the Apollo 15 landing site in this mountainous region. So here's a higher resolution image taken from orbit. And here's an EVA map. EVA stands for extravehicular activity. They were there for 3 days on this flight, and here's the landing site. And they took that roving vehicle on an EVA for every one of the, EVA stands for extravehicular activity. It went outside 3 times. And here you see this is 2 kilometers. So it gives you an idea. They went miles from the landing site to collect rocks and take pictures and stuff. And, oops, okay, let me do this. Well, now it appears to be better. Here's a photograph taken on EVA-2, and that right there is the landing vehicle. So you can see how far they went in an effort to do the scientific exploration. Okay, so over the 6 flights, about 163 man-hours were spent in their spacesuits outside of the lander on the surface. And most of that time was concentrated on scientific research, setting up scientific instruments, gathering samples, taking pictures. And in fact, some of the time they were kind of rushing around trying to get as much done as possible, because 163 man-hours is not a lot of time to study an entire world. And they were trying to get as much done as possible, because it's the only time people have ever been on the moon. And you can see here he's using an instrument to collect a rock sample. I got a few other images of things. Now here's some of the rocks they brought back. These 2 are volcanic basalt, so volcanic rock from those darker areas. And these 2 are anorthosite breccia. Breccia is a type of rock where you have a bunch of broken pieces embedded in some kind of matrix. So anorthosite breccia is a broad category of rock that I guess includes most of the rock that's on the surface of the moon. So they brought back a total of about 400 kilograms of rock. That's like 880 pounds. So a lot of samples, and they've become very valuable. Here's some lunar dust. The whole moon is covered by a very powdery, fine, dusty material that they called soil because of the incessant impacting on the surface of the moon by meteors. And they also set up these scientific instruments. They had these platforms of instruments connected to a central hub, and they had a variety of different types of scientific instruments. Here's another view of one of these packages. And if you look at some of the names of the instruments, like heat flow experiment, lunar seismic profiling experiment, lunar surface gravimeter, geophone, these are the kinds of instruments you would expect a geologist to use to study the crust of the Earth, because most of the science that they were doing was geology related. And so there are some other instruments like lunar atmospheric composition experiment, lunar ejecta and meteorites experiment that you wouldn't use on Earth to do geology here. But these are the kinds of things they took. And they were powered by a little nuclear reactor that kept them rolling for months after the astronauts left. And some of these instruments were being used for a long period after the astronauts left. In fact, one of them is still used today, one that doesn't require any power. Let's see, I got another film. And this is, I just want to show you, this is just a collection of video clips from EVA moments on the surface. Just to give you an idea, it's kind of a random smattering from EVAs during Apollos 15 and 16. To give you an idea what they were doing on the surface. So let me see if I can get this to go.
Yesterday, we can see the horizontal bit. Yeah. Good boy. Good. I'll be jumping. Okay. Don't be too careful. We're going to see person who starts the explosion. Okay, Houston. If you want my opinion on the thing, I don't think we're hitting hard ground. I think what I did is probably hit a rock. And I should probably move this thing over a little bit. Okay, we'll just go with the 2/10 and see how that does. Just use a little more water. I think it's a size of that rock. Well, you can see. Once I get to it, the bigger it is. Look at this. Tony, this is a black matrix with some excellent crystals in it, and also that are milky in color. Don't see any cleavage though. Our stripe is about a centimeter across, and it has a matrix of a white, that white rock like up on the rim, not a matrix, but some class of that. Okay, magazine Bravo is going on the commander's camera. I just tried to blow off the dust, Tony.
So there's just a few scenes from, there's probably 90 hours of video from all that stuff, which you can watch in one form or another. Okay, so now there was also research done from orbit. As I said, there was 2 spacecraft. This is the command and service module, the one other than the lander, and it remained in orbit around the moon while the 2 other crew members were on the moon. There was 1 person in this. And it turns out there's some research you can do from orbit. There's cameras, mapping cameras to take lots of pictures, a laser altimeter that shoots many laser beam pulses down to the surface, and the amount of time it takes to reflect back up can be used to measure the altitude, which do that 1,000,000 times and you build up a topographic map of the surface. But also things like there's a gamma ray spectrometer. The moon doesn't have an atmosphere, and so its surface is constantly being bombarded by cosmic rays, high-speed nuclei from outer space, and that excites nuclei on the surface of the moon, causing them to emit gamma rays. And if you're flying over the surface and you use a gamma ray spectrometer, you can identify the types of nuclei on the surface, the types of isotopes that exist there. So you can get some information on the composition of the surface just by flying over as you're orbiting. And these kinds of instruments have been used on a number of subsequent robotic missions, like to the planet Mercury and Mars, and also more recent ones to the Moon. You know, much more modern, advanced type of electronic equipment. So, this is some kind of research that was done from orbit as well. And of course, this whole thing was mostly controlled from the ground. It was discovered early in the space program that you could manage most of the complex processes on board from telemetrically from the ground. And you know, these were the flight controllers. There were these technicians. Each one would monitor a certain subsystem, so the astronauts didn't have to manage everything that was going on board. So this is during one of the Apollo 15 EVAs. Okay, so what's been learned from all this scientifically? Well, lots of things. I want to talk about just three. One is the history of impacting in the solar system. In other words, we've learned something about the history of meteor impacts on the surfaces of the planets. And that turns out is important for understanding the history of the planets. Also, what was learned has provided clues to the moon's origin. What is the mechanism that generated this big moon orbiting the Earth? And finally, they brought up lots of information from the surface that can be used to calibrate data taken from orbit around the moon by more sophisticated laser probes that don't have direct access to the surface. So those are the three things I want to talk about. Okay, so first, the history of impacting. This is a pretty wide section of the side of the moon that faces us. It's over 1,000 kilometers across, and it's covered with these impact craters. These round things are all impact craters from the theft and pummeling that the moon has experienced over the history of the solar system. And for 250 years, it's been thought by astronomers that the planets in the solar system formed from a disk of material that was orbiting the newly forming sun. And that material clumped into larger and larger bits until you finally had planets. And if that's the mechanism that gave rise to this planetary system, you would expect that there would be leftover material from the formation of the planets early on, and that stuff would be slowly collected on the surface of the planets. And so the oldest places you would expect to be very heavily very heavily cratered. And that is, in fact, what we see. So it would be nice to be able to characterize the history of impacting since the formation of the planets. In other words, what has been the rate of impacting as a function of time through the history of the solar system. So to that end, you can see, looking at this picture, that there's a heavier impact crater density over here than over here. And that's not because more impacts occurred here. It's because volcanic activity in this region has covered over, at some point in the past, covered over the impact craters that were there, so that all the impact craters you see in this region have formed since the time of that volcanic activity. And all the craters over here have been formed since that surface was formed by volcanism or sedimentation or whatever. So if you have enough of these regions of differing age, you can count the number of impacts on the regions of differing age, and from that, infer the rate of impacting as a function of time, so to get a history of impacting for objects in the solar system. Okay? But that only works if you know the ages of these things. In other words, how long ago did this volcanic activity occur? And about the only way to do that is to go down to the surface, pick up rocks, bring them back to Earth, and study them in laboratories with radiometric methods that geophysicists have developed to find the ages of rocks. And by the age of a rock, I mean the amount of time it's been since that object is a solid object, since it cooled from molten lava or formed by sedimentation. And that's been done for tens of thousands of rocks on the Earth, so they did it for these rocks from the moon. And here's just the result of the dating of one of these rocks that were from the moon. This is two different radiometric methods using two different radioactive isotopes found in the rock. And they fortunately found the same age because it's the same rock. But basically what you do is, in a rock, you take a bunch of samples out of there, and in each sample you measure a number of different isotopes and take some ratios of those isotopes to each other and plot a graph where each point is a sample within the rock, and the horizontal position is one ratio, the vertical position is another ratio. And it turns out the points line up, and the slope of the line is related to the age of the rock. It's a very slick method. It's called radioisotope isochron dating. And it's a very robust method in that there's no other plausible reason why the points should be in this straight line, this sloped straight line, except that the rock has the age as told by this method. So, and you can see for this one, 3.57, that's in giga years, billions of years. The rocks from the moon are systematically much older than rocks on Earth because the Earth is still internally active and it's always reprocessing its rocks. So most of the rocks on the Earth are much younger than the Earth itself. So let me show you some results from this. Okay, this is the anorthosite breccia rocks taken from different places. So Apollo 17 landed in one place, Apollo 16 in a different place. Luna 20 is actually a Russian robotic mission. And so you can see these rocks from different places, but and each square represents a rock, the age of that rock sample. And you can see that they're all roughly the same as each other, around 3.94 giga years. So most of the rocks from the surface of the moon have about this age, and that's taken as the age of most of the surface of the moon. You can see that there's some older, some much older, some younger, but for the most part, they all cluster around this age. But if you look at the volcanic rocks, these are different in the different places where the rock came from. So see, here's 3 giga years, and there's 4. So they have different ages, and that's because these volcanic events that covered over the surfaces occurred at different times in the history of the moon, and so they brought back these rocks of differing ages. So we do, in fact, have regions of varying age so that we can, from the crater density on there, infer what is the changing impact rate over this history. And let me just show you the bottom line of this. So this graph, I got these graphs in different places. The time axis is backwards. Here's a brand new surface, and here's really old surfaces. So the vertical axis is the density of cratering on the surface. What they've done is count the craters that are bigger than a kilometer in diameter. So these are big craters. And count how many of them there are per square kilometer in a region, and then plot that as a function of the age of the region. So you can see the young places have fewer craters, and then as you go to older and older spots, more and more craters. Now this is a logarithmic scale. Every notch you go up is another factor of 10 higher crater density. So it's a little difficult to see what this implies, but I've taken this curve, which is kind of a fit to the data, and I've put it on a plot of linear scale, and it looks like this. So for brand new surfaces, the youngest surfaces, you see there's no craters, and as you go to older surfaces, it goes up, right? More and more craters per square kilometer. And from brand new surfaces to surfaces that are maybe 3.3 giga years old, you see that the density of cratering on the surface is about proportional to the age of the surface, right? It's a straight line. So the density of craters is proportional to the age of the surface. That's what you would expect if the rate of impacting over that time period had been constant, right? If it had been constant, then two surfaces differing by a factor of 2 in age would also differ by a factor of 2 in number of craters on the surface, right? So from this, it appears that for the past 3.3 giga years, the rate of impacting on the surface of the moon and the other planets has been roughly constant. But as you go toward earlier times than that, the slope gets higher and higher and higher. And as the slope gets higher, that means there was a higher rate of impacting at those times. Now we know from other radiometric methods on Earth rocks that the solar system is about this old, about 4.6 gigayears. So you can see from the beginning of the solar system, there was heavy impacting, and this line goes off, much later than 4.6. So heavy impacting, and then it slowed down until about 3.3 gigayears ago, slowed down to the present rate of impacting, and we still have impact on the planets. Okay, so this is a valuable set of information here because it tells us something about the formation of the solar system and the history of impacting on the surface, but it also can be used, this graph can be used to interpret some things about the history of the other planets, because nobody's ever brought rocks back from Mercury before, the planet Mercury, and so we don't know the ages of the rocks from different areas, but now we know the rate of impacting as a function of time in the solar system. So you can look at a map of Mercury. There are probes that orbit, well, it's a probe orbiting Mercury now. We know the density of craters at these various places. You can say, okay, such and such density of crater, that means it's this age, right? We can use this graph to do that. Now, the other planets are at different places in the solar system. They're different sizes, so that's going to affect this distribution. But with a few assumptions, you can come up with a similar graph for the other planets. So, in other words, now it's possible for people studying the geologic history of these other planets to look at a map of the planet and say, okay, this region is 2.7 gigayears old. This region over here is 3.9 gigayears old. That's one of the things geologists need to know to understand the evolution, the geologic evolution of these planets. So this was a major piece of information for understanding the history of at least the terrestrial planets, the Mercury, Venus, Earth, Mars, and so this is probably the most important scientific thing that was learned as a result of the Apollo research. Now, another thing is the actual mechanism that formed the moon. The moon's mass is about 2% the mass of the Earth, which doesn't sound like much, but compared to the other natural satellites in the solar system, the other moons of the other planets, that's very big with respect to the planet that it orbits. There are 6 other planets in the solar system that have moons, and for each I've taken the heaviest moon. Earth just has one moon, but the others have more. I've taken the heaviest one of each and found the percent of the planet that it orbits, just the percent mass of that. And you can see that, the moon, at 1.2% the mass of the Earth, towers over all the rest, right? You can't even see the thing for Mars' biggest moon. Mars has 2 moons, but they're tiny, millions of times less massive than Earth's moon. So it's, tiny fraction of the percent of the mass of Mars. Jupiter and Saturn both have moons that are heavier than our moon, but those planets are enormous compared to Earth. And so those moons are a tiny fraction of the mass of the planets themselves. So you can see the moon is kind of unique in the solar system. And it's actually difficult to understand. As a result of this size, nobody really knows for sure what is the mechanism by which it formed. These other moons, like the extensive moon systems of the Jovian planets, it's pretty well, their nature is pretty well consistent with their forming from a mechanism that's kind of a smaller version of the way the planets formed orbiting the sun. A disk of material orbiting the new planet from which these moons form. Models based on that work pretty well to describe the moon systems that they have. But that doesn't work for the Earth and its moon. It appears that some other mechanism is responsible for the formation of the moon. And it's an important question to understand because, for one thing, the moon is thought to be necessary for the stability of conditions on the surface of the Earth that has allowed life to exist here for 3.5 billion years. So if, most people would like to know if there's life on planets orbiting other stars, right? Where would you look? Well, if the moon's necessary for stability of conditions on the Earth, then one good place to look would be a planet like the Earth that has a moon like the moon. And so it would be nice to know how the moon formed, because if it's a very unusual process that formed the moon, then maybe a system like the Earth-Moon system is very unusual in the galaxy or in the other galaxies, and maybe life is not so common, or at least life as we know it. So, that's one reason you want to know how the moon formed. And one clue to that, how the moon formed, is these are the 5 most abundant elements in the moon and also in the mantle and crust of the Earth, oxygen being the most abundant element. And you can see that the ratios are roughly similar between the moon and the Earth's crust and mantle. So they appear to have formed from the same storehouse of material. But it's not just the elemental abundance, but the isotopes of those elements. Oxygen, there's 3 isotopes of oxygen that exist in the Earth and in the moon. Oxygen, the oxygen in this room, oxygen is the most abundant element in the mass of the Earth, because rock is, by weight, mostly oxygen. But there's 3 isotopes, oxygen 16, 17, and 18. 16, each nucleus has 8 protons, 8 neutrons. 17 has 8 protons, 9 neutrons. 18 has 8 protons, 10 neutrons. And all of those exist on the Earth. It's mostly oxygen 16. This is a pie graph showing the relative abundance of these things. And the blue piece of pie is oxygen 16. And the red one is 17. And I don't know if you can even see the green piece of pie, but it's in there somewhere. You can barely see it. So they're far less abundant than oxygen 16. But the relative abundance of these isotopes varies from one rock to the next on the Earth. And I'll show you, there's an interesting pattern to the way they vary. So this is not real rock data, but real data is similar to this. Each one of these points represents a rock. So this point, for example, they took a rock and measured the abundance of these 3 isotopes of oxygen. And this rock, its oxygen 17 to oxygen 16 ratio is 2 parts per thousand greater than the same ratio for seawater. Seawater is like the comparison of oxygen abundance for all this stuff. And the same rock, its ratio of oxygen 18 to oxygen 16 is like, what, 3.7 parts per thousand greater. For the formation of the moon. And when it was discovered that the moon's composition is so similar to the Earth's mantle, a single formation mechanism became, the primary candidate that most people think is the formation mechanism that formed the moon, and that is what's called the giant impact hypothesis, where another planet formed a similar place in the solar system and then smashed into Earth. Now, this is a plausible event. I mean, it could have happened. There could have been more planets in the solar system at the time. And in simulations, people have done extensive computer simulations of this type of event. And at a certain angle and a certain size object, it successfully forms a system like the Earth-Moon system. Pieces of the material from the Earth's mantle are blown off and they come together by gravity, and the Moon forms from that. So it's simulations of this are very successful at forming a system like the Earth-Moon system. And sort of a sub-category of this is an object formed at one of the Earth's Lagrange points in its orbit. So these two places in the Earth's orbit where something can orbit semi-stably, and then it escaped from that location, smacked into the Earth. The angle that you would get and the impact energy that you would get are particularly consistent with what we see, according to the simulations. In other words, this could successfully form the Earth-Moon system. Now, as I understand it, there's still problems with this model. I mean, there's things that it can't really explain, aspects of the Earth-Moon system, but it is at present the most commonly accepted mechanism for the formation of the Moon, this sort of great big impact event. So if this is how the Moon formed, we know a little bit more about how you get a system like the Earth-Moon system, maybe how common that is in the galaxy. And the last thing I wanted to talk about, I just want to briefly touch on, this is a map of surface composition made by a probe that orbited the Moon in the last 10 years. And the colors indicate different mineral compositions on the surface. So we've learned, since the instrumentation has advanced since the 1960s, we've learned a lot more about the composition and the properties of the Moon's surface. But of course, since this probe could not touch the surface, the information had to be calibrated by data taken directly from rocks from the surface. So, for instance, the Apollo 11 landing site is like right in here somewhere. We calibrate the colors here with the actual composition of the rocks brought back by the Apollo 11 astronauts. So, and this is quite important, apparently, in the people that study the geology of the Moon, to be able to calibrate this data using the data brought back by the Apollo astronauts. Okay, so those are the three main scientifically significant things that I wanted to discuss. And I just want to show you this one last graph. This is the cumulative number of refereed professional journal articles on scientific discoveries based on the research done during the Apollo flights. And not surprisingly, when the flights began early in the history of Apollo, the number of publications increased fast, slowed down after a while, but you can see that it's still going up. We're not up to 2015. I guess it's a couple of years old. In other words, the information that they gathered, the rocks that they brought back and the stuff that they learned is still important in research on our knowledge of the Moon, because there's still publications being published based at least partly on what they learned. So there's a rich scientific legacy to this, and I think it's interesting that a project born in the Cold War, born in the violent nature of mankind, has helped us learn something fundamental about our place in the universe. It's a very 60s kind of thing. So thank you. So anybody have any thoughts or questions? Giga-year is a billion years. Yeah, like a gigabyte is a billion bytes of data. Giga is the metric prefix for a billion. Yeah, geologists and astronomers use the unit of time giga-year. There's no stars because for the same reason that you don't see stars in photographs taken on the Earth during the day, because the exposure of the camera is way too low for that. Most people think that you don't see the stars because the sky blocks them out. It's because stars are faint. You know, our eyes have to adjust a lot to see the stars at night. And you know, when you walk out of a bright room at night, you don't see stars, right? But then your eyes adjust, and you start to see stars. If you look at a picture taken at night on Earth in a bright location, let me see. Let me just look at. So here's, I'm just trying to find a picture. Okay, stadium night. There's a picture taken of the night sky at night. Now maybe this is a little, hey, we don't see any stars here either. And it's because the exposure of the camera is set for the bright light of this. And this is probably a good bit fainter light. In other words, a higher exposure than you would get during the day. So almost, I don't think there's any of the Apollo photography from the surface has any stars in them. That's just because the stars are too faint. Mm-hmm. Okay.
Why don't objects and asteroids hit Earth the way they do?
They do. At just the same rate that they do, probably at a greater rate than they do the moon. The Earth has relatively few impact craters because it's internally active, it has weather, and it has geologic activity, which erases those things over time. But there are impacts. There hasn't been, you know, this one a year ago in Russia. There was a huge impact, exploded over Chelyabinsk, or what was that place? And it broke a bunch of windows and stuff. But there are impacts. We don't think of them as very frequent because the time scale over which human civilization has existed is so short compared to the time scale of the history of the solar system. So, yes.
The Apollo missions wouldn't have taken place without the motive of the Cold War.
Right.
Right. So it was essentially politically motivated.
Yeah.
And so it's hard to imagine a president today going before Congress and saying, I propose the most difficult and expensive project ever undertaken. Doesn't this bode very badly for scientific research going forward?
Yeah, maybe so.
It's a political question.
Yeah.
And so your very informative talk began with the recognition that the whole U.S. space program is politically motivated,
Mm-hmm.
scientifically motivated.
Yeah.
And consequently, scientists and other people interested in truth
Mm-hmm.
have got to live in a relation to a political world. And so where does the will for scientific research come from if it's not motivated
A war.
by fear of
Being blown up.
nuclear destruction or lust for profit?
Yeah, that's a good question. I mean, you know, it probably wouldn't have happened as, you know, except for the Cold War. And the fact that, you know, the rockets were developed as ICBMs, I mean, that all that technology came directly out of the Cold War.
Well, and World War II.
Yeah, and World War. Right. Yeah. Right. Yeah, you know, I mean, there's still a lot of money spent on space. While we now have the International Space Station overhead, it's much more complicated than Apollo was, and has been more expensive. But that cost has been spread over many years. Certainly not the same kind of adventuresome, you know, attitude as they had back then. But I will say that even back in the 60s, there was there was attempts to slow this down and stop it. I mean, in fact, there should have been an Apollo 18, 19, and 20 that had all this stuff built, and it was canceled before the flights were finished. That's why you can go to the Marshall Space Flight Center and see a Saturn V, because it wasn't used for the flight that was slated for. So, I mean, it was true back then, too.
Have a similar number of publications come out of the International Space Station as have come out of Apollo?
I don't know. I would say, I don't know. I would say probably. That's a good question. I don't know. I'd like to see a similar graph. You know, most of the research, I mean, they're doing important research, but it's mostly focused on future space flight. You know, how to cross interplanetary space and go to Mars, and you know, to see what effect it has on human physiology. I mean, there is fundamental research being done up there too, but it's mostly focused on space flight. But the space station is, I mean, it's a really, really ambitious effort. Mm-hmm. I hope so. It's you know, it's going to take. It's so expensive to go into space. It's like $10,000 a pound just put something into orbit around the Earth. That's a lot of money. And so far, the only business ventures that have proved profitable based on that are like communication satellites. And in fact, most of the satellites that are in space, probably, you know, the vast majority of them, are military satellites which are paid for by governments. And so, you know, there are efforts to try and decrease the cost so that more people will be motivated to venture out into space. But, you know, I certainly hope to see that occur. We'd have to come up with new technology to travel across to other stars. It's so much farther. I mean, the moon's 250,000 miles away, but that's literally, I mean, the nearest star is, I don't know what the number would be, probably 1 billion times farther than that. We've really just gotten our ankles wet in the sea. Uh-huh. I don't know, money, I guess. I think somebody figured out a way to profit on space flight, like space manufacturing. I mean, it's been suggested, like back in the 80s, people thought that space manufacturing was going to, you know, let me back up. There's certain things that are much easier to manufacture in zero gravity than. Well, I mean, you mean it took away space manufacturing or whatever? Well, I mean, there are plenty of people that would love to travel in space and explore the universe. It's mustering the resources to do it. It's convincing the people with gigantic amounts of money to pay for it. You know, that's, I mean, every time NASA has to go to Congress and beg for money to do everything that they do. And so that's the question, I guess, is how do you convince people to control huge quantities of money to spend it on exploring space? But I think what it's going to take is somebody to make space flight profitable. You know, probably some sort of space manufacturing. Seems to me, that's my limited knowledge opinion. So, mining on asteroids, yeah. Well, of course, the asteroids, the asteroids are a lot richer in the rare elements than is the crust of the Earth. And so if it could be, if somebody could figure out how to make it profitable and economically practical to bring that stuff back to Earth or to use it in space, in a way that makes it cheaper than getting it on the Earth, then yeah, it can work. And the more we lower the cost of space flight, which is what some of these private companies are now trying to do, the closer we get to that point. But I can't give you any predictive number on how. Well, I mean, it's if we ruin the Earth, we can't really go anyplace else, if that's what you mean. This is the best place we got. We don't even know of another planet that's anything like the Earth, and if we found one, it would be so far away that we can basically say it's impossible to get there, or at least impossible. Is that what you meant? Or, mm-hmm. Well, what's happened on the moon has happened on the Earth. The moon is different because it doesn't have an atmosphere. It's much smaller, so it's internally inactive at this time. So it records on its surface the deep past of the Earth-Moon system. The Earth was like that back when the solar system was young. And, you know, that graph that I showed where the impact rate was high for the first billion years or so, that's the period when there was no life on Earth. So the Earth was inhospitable for that extended period of time, and then the impact rate slowed down. Then we had life. Now, the oldest evidence of life is, what, 3.5 billion years old, something like that, huh? So it's, but to answer your question, yeah, I mean, I guess the more we know about how the planets work, you know, the better we can deal with problems we have with this one. Yeah.
Why is the problem with the existence of Earth necessary for life?
Because it has stabilized the rotation, the orientation of the rotation axis of the Earth, and so the tropics have remained tropics and the poles have remained poles over the whole history of the Earth. If it hadn't been for that, there probably would have been periods where the rotation axis would have varied a lot, and you just wouldn't have these stable conditions. I mean, perhaps that isn't really necessary, and perhaps life could have flourished anyway, but it's thought to have, you know, been necessary for these stability conditions, which is real interesting because, you know, it would be nice to know how common systems like this are. You know. Mm-hmm. No.
Why was there one year?
She was my wife. Because when the solar system first formed, it's thought that the planets formed from a disk of material orbiting the young sun, and this material clumped into larger and larger bits until you finally had planets. So there were lots of smaller bits left over from the formation of the planets, which then continued to impact the planets over time, and until they got mostly collected up. Uh-huh. If they didn't have our moon? Well, if it's, you know, if you had a system out there orbiting another star and a similar composition to the Earth and a similar, you know, one might assume that the history of the conditions on the surface would be similar. And, you know, there are many things about the history of the conditions on the surface of the Earth that had to go kind of right in order for life to have survived well for as long as it has. So the moon is thought to be one necessity, but there are other things as well. And so that's one factor, I think, the moon, that can make conditions like they've been on the Earth. Does that answer your question? Okay. Yeah, did you have a question?
Yeah, I was thinking about your comments on the theory about forces. I think my that is more impacting on body forces.
Yeah, I guess that's the general trend. Closer to the sun, there's more stuff, and you know, I don't know what exactly is the relationship between distance from the sun and rate of impacting at any given point in time, but I think that's the case. Yeah. And it has to do with the size of the object too. Like Jupiter soaks up a lot of stuff because it's so big. You know, it has this huge gravity. Thanks for coming.